Geometric probability. So sometimes you can use a model in which you let points represent outcomes. You find the probabilities by comparing measurements of sets of points. So to sum that up, let's take a look at the length probability ratio. This is telling you that the probability of an event happening, this is the notation we use right here, is found by the length of the favorable segment, meaning the length of the segment that you are looking for something to happen on, or whatever the case may be. So length of the favorable segment divided by the length of the entire segment. So my example here is, what is the probability that point E, which obviously we don't see listed, but point E is on segment BC. So we want to know specifically, what is the probability that point E is going to fall between these 2 points? And you find the probability by setting up a ratio of the segment length BC divided by the entire segment length of AD. So let's just jump right down to the examples so this makes more sense in context. So the first example set uses this segment here. And you can see that you have smaller segment lengths of JK, which is 3, KL, which is 7, and LM, which is 4. This gives us the total length of the entire segment of 14 when we add up those 3 numbers. So this problem, number 1, is saying, what is the probability that point X is on segment KL? So we want to know what the probability is that there's a point on KL. Again, this is notation. We write it just as you see it. And we set up a ratio, which is going to be segment KL divided by the entire segment length, which is JM. When I substitute values in for this, we have 7 for the length of KL and 14 for the total length. This simplifies to 1/2. So 1/2 as a decimal is 0.5, or we would say a 50% chance. So to answer this question, the probability that point X is on segment KL is a 50% chance. This is what we're looking for. Let's take a look at number 2. Number 2 asks for the probability that X is on segment LM. So what's the probability that the point will fall in that green highlighted segment? When I write out the ratio, we have the segment length of LM divided by the segment length of JM, which is 4 over 14. 4 over 14 simplifies to 1/7, and as a decimal, 1/7 is 0.1429. So as a percent, we'll say 14.29%. If anyone forgot, just a quick reminder, a decimal to a percent, move the decimal place over 2 places to the right, and that is going to give you your percentage. So there's a 14.29% chance that point X is on segment LM. Okay, let's look at a real world problem where we can use a number line in order to find the probability that a Chicago Transit Authority train arrives or departs a station every 15 minutes. So we are assuming that we arrive at Addison Station on the red line at random times. What is the probability that you will have to wait 5 or more minutes on a train? Okay, we need to dissect this completely. So we need to go right back up and understand what the initial situation even is. It says a Chicago Transit Authority train arrives or departs a station like Addison, that's an example of a station, every 15 minutes. So I'm going to do a number line for this. Here's my number line. The train leaves every 15 minutes. So here we have 0 minutes. And here we have 15 minutes. Since the train arrives every 15 minutes, this number line will repeat over and over and over. Because part A is asking what is the probability you will have to wait 5 or more minutes, let's break our number line into increments of 5. So we have 0, then we'll do 5, then we'll do 10, and then lastly we have 15 minutes. If this is our number line, 5 or more would be between 5 and 15. So when I set up the probability of waiting more than 5 minutes, I'm going to set up a ratio for this. That is the entire segment length I just highlighted in green. That would be 10. That's a total of 10. Divided by the complete length, which is 15. When I simplify this, it simplifies to 2/3. When I write it as a decimal, it's 0.67 or 67%. So to answer this question, I would say there's a 67% chance you're waiting 5 or more minutes. So you're waiting between 5 and 15 minutes. After 15 minutes, a new train arrives. So our number line only includes the amount of time you could wait between trains. But between 5 and 15 minutes could be up to 10 minutes that you're waiting, and you have a 67% chance that you are waiting for that long. Let's look at part B. Part B uses the same problem, and it says, what is the probability that you will have to wait between 0 and 10 minutes for a train? So we're waiting 0 minutes to 10 minutes for a train. That means we're looking for the probability of waiting between 0 and 10 minutes. And we're looking at this the same way. So between 0 and 10 is obviously a segment length of 10 minutes. The total amount that we could possibly wait is 15. So that's the same percentage. It's a 0.67% or 67%. Oops, I said that wrong. It's 0.67 as a decimal or 67% of waiting time. Now you could look at this anyway. What if I asked you what's the probability of waiting between 5 and 10 minutes? Well, that would only end up being a 33% chance. You could probably look at this number line and determine that. If you had to break it down to individual minutes, you could figure that out if you want to. Just use it as a number line. Every dash or every tick mark on the number line would represent your minutes. I want everyone to press pause and try the on your own section by yourself. For the first problem, or part A in the on your own section, we're looking for the probability that when someone tries to pour a glass of tea from the container, it is below 2 gallons. That means it would be between 0 and 2. So on our number line, we're going to use a segment of 2 divided by the total segment length of 8 gallons. 2 over 8 simplifies to 1/4, which is 25%. So there is a 25% chance that the container will be below 2 gallons. And for part B, what is the probability that the amount of tea in the container at any time is between 2 and 3 gallons? So between 2 and 3 is located here on the number line. That would only be 1 out of 8 gallons that could potentially fit in the holder. So 1 out of 8 is 12.5%. So you have a 12.5% chance that when you go to pour a glass of tea, there's between 2 and 3 gallons left in the container. Okay, next we're looking at the area probability ratio. So very similar to the previous examples we went over, but now we're dealing with area. So we will be looking at the probability of an event happening in a favorable area, and the equation is going to be the favorable region divided by the entire region. So for my example, I said, what is the probability that point E is going to be in circle B? So I need to find the area of circle B and the area of the rectangle A, and that will be my ratio. So to model some real world problems, this first one here does require a list of different area formulas out on the side. But let's first analyze and sketch a diagram of what we're working with. So this says, suppose a skydiver must land on a target of 3 concentric circles. If a diameter of the center circle is 2 yards and the circles are spaced 1 yard apart, part A, what is the probability the skydiver will land in the red circle? Okay, I need to draw this for everyone to see. So here's what it's talking about when it says concentric circles. It means circles within one another, kind of like a target, or you could say a bullseye. Let's make these bigger. All right, the directions say that the diameter of the center circle is 2 yards. So the diameter is from one side to the other, and it's 2. But then it said the circles are spaced 1 yard apart. Okay, well, if the diameter of the first circle is 2 yards, that means the radius is 1 yard. And then we have, for the next circle, 1 yard apart. And for the next circle, 1 yard apart. So if I highlight the interior circle as purple, let's use red because it says it's red. If I highlight the interior circle as red, and then I'll highlight the second circle as gray. I know it's white in the photo, but just so we can use gray as our coloring. And then the exterior circle we're going to highlight in blue. What we need to do is we need to find the area of all of these circles. So we need to find the area of the red circle. We need to find the area of the gray circle. Imagine that the red circle isn't there at all. And then we need to find the area of the blue circle. We're going to need those to answer all of the parts. So first let's start with the red. So the area of the red circle. This is going to be, or when we use the area formula for a circle, it's pi times the radius squared. So this will be pi times 1 for the radius squared, which is equal to 1 pi, or just pi. Next, let's find the area of the gray circle. This is going to be pi times the radius squared. Well, the radius of the gray circle is 2 yards, because remember, the gray circle is this entire circle. All right, I know the red circle is inside of it, but when you're finding the area of the gray circle, you need to find the area of the entire shaded region. So to get to the center, we have 1 yard here plus 1 more yard, which gives us a radius of 2 yards. So pi times the radius of 2 squared, and this is equal to 4 pi. And then lastly, we need to find the area of the blue circle. So same thing, we're looking for the total area of the blue circle, which is pi times the radius of 3. We have 1 yard to 3 yards. So pi times 3 squared, which is equal to 9 pi. Okay, we're going to use these and we're going to have to apply different properties for each of these parts that we're going to be solving for. So part A, what is the probability that the skydiver will land in the red circle? So the total area of the target is the blue circle, which is 9 pi. So the probability of landing in red circle is going to be the area of the red circle divided by the total area. We just found these. The area of the red circle is pi. The total area is 9 pi. So we end up with pi over 9 pi. Of course, those values of pi are going to be eliminated, leaving us with 1 over 9. And 1 over 9 is 0.11 or 11%. So there's an 11% chance that the skydiver will land in the red circle. Okay, part B, the probability that the skydiver lands in the blue region. So the blue region is not the entire circle if you look at the model that's shown on my page here. The blue region is just that outer circle. So we need to literally find the area of just this blue outer circle here that I'm highlighting. So how we could do that is we can take the area of the blue circle and we could subtract the area of the gray circle to give us that outer ring of area. So we have area of blue minus the area of the gray, which is white, and that's equal to 9 pi minus 4 pi, which is 5 pi. So the probability that the skydiver lands in the blue region is the partial area of that blue circle I highlighted, 5 pi, divided by the total area of the entire circle, which is 9 pi. Our values of pi will be eliminated, leaving us with 5 over 9. And 5 over 9 is 0.56, or 56%. And what is the probability that the skydiver lands in the white region? So that was where I used my gray highlighter. Once again, just landing in the white region means we need to eliminate that red circle. So we need to find the area of the gray circle, which we already found, minus the area of the red circle to get just that perimeter or the outer white circle where the skydiver could land. So this would be 4 pi minus pi, which leaves us with 3 pi. The probability that the skydiver lands in the white region is equal to 3 pi over the total of 9 pi. Eliminate your values of pi. 3 divided by 9 simplifies to 1/3. So this would be 0.33 or 33%. So a 33% chance. So to review our answers quickly, the probability that the skydiver will land in the red circle, which is the center, is 11%. The probability that the skydiver will land in just the blue region, so the outer blue circle, is a 56% chance. And the probability that the skydiver will land in just the outer white region is a 33% chance. Moving on to our last example set. This says that you can also use angle measure to find geometric probability. The ratio of the area of a sector of a circle to the area of the entire circle is the same as the ratio of the sector's central angle to 360. So What that means is, well, let's just jump down to number 1 so you can see what I'm talking about, and then we'll come back up and read that definition. So an entire circle measures 360 degrees. Part 1 says probability that the pointer lands on yellow. So we can use our angle measures. If yellow is 45, that means 45 is actually this angle right here that I just marked. So we can set up a ratio of 45, which is a portion of the angle, or a portion of the circle, divided by the total circle, which measures 360 degrees. And this simplifies to 12.5% when you type it into your calculator. Well, it's 0.125 or 12.5%. So if we come back up to this definition after we've gone over that one, the ratio of the area of a sector of a circle to the area of the entire circle is the same as the ratio of the sector's central angle, so in this example it was 45, to 360, which is your denominator. So for problems like this, if you have angle measure in a circle, a full circle, that works out nicely. It ends up being quick problems that you just use the central angles for. All right, the second problem says the pointer landing on purple. I know this is like a terrible color. It was better on my computer originally, but this right here is the purple section. This one. Oh, you can't see that. It's the 105. So 105 is the central angle of the purple section divided by 360 is going to give you about 0.29. So we're going to say it's 29% chance of landing in the purple region. And the third example says, what is the probability of the pointer landing on neither red nor blue? Which means we do not want the pointer to land anywhere in these regions here. So we need to eliminate them. Well, what's left? So we need to find the remaining angle measure and divide that by 360. So we have 105 plus 45 plus 90. And this is equal to 240. So this tells us that we're going to set up a ratio of 240 because that's the remaining central angle after we get rid of these two colors we don't want, divided by 360, and this is equal to 0.666, so we're going to say 67%. And that's how you use angle measures and a circle to evaluate probability. Again, we're just looking at some basic examples. Obviously, this goes much further in depth, but in general, we just looked at geometric probability of line segments and how you can apply them to the real world, area and how you can apply them to the real world, and then angle measures, which you use central angles, and then the total of 360 and how you can apply that to the real world. So there's 2 more questions in the On Your Own section that have to do with this spinner. So if everyone could press pause and answer those by yourself, come back together and check your answers, or come back to the video and check your answers, and please let me know if you have any questions.